Okay. So I'm Taro. Okay, it's okay. So I'm Taro Nakamura. My name is Taro Nakamura in Chu University, Japan. I'm chair in this session, and it's please wait. This session we discuss the outdoor in the field robotics, and this session has 1, 2, 3, 4, 5, 6 presentation, and each presenter has 15 minutes and 20 minutes for a presentation and 3 minutes for a question time. Okay, so this is the last session today, and please discuss. Please discuss and a good presentation, I hope. And the first presentation is horizontal drilling with shield robotics explorer, as presented by Mr. Tokoi. Please prepare. No, I can't hear you. Yes, please. So someone said, please say something. No, I can't hear your voice. Please. Okay. Okay, I can hear you. Please.
Thank you for introduction, Chairperson. I, Ryosuke Tokoi from Chu University, will make a presentation on this title. Here is the outline of my presentation. First, I'd like to provide some background for my study. Recently, scientific investigation of the ocean has been actively conducted. Seabed mineral resources can be found at the bottom of the ocean. To utilize these resources, it's necessary to collect and analyze samples. Sampling of marine resources helps to clarify how marine resources are generated and distributed. To sample seabed mineral resources, vertical drilling is generally used. However, this method has two problems of low efficiency and large cost. To solve these problems, we aim to develop a seabed robotic explorer that can excavate horizontally and sample seabed mineral resources. At present, several drilling robots have been proposed as shown in Figure 1. However, many existing drilling robots are susceptible to earth pressure and cannot be discharged out of the hole. Therefore, these robots cannot excavate deep underground. To solve these problems, we developed a drilling robot based on earthworm locomotion. The static motion of earthworm is locomotion method as shown in Figure 2. This motion has some advantages on excavation. It enables to move narrow space, not to be susceptible to earth pressure, and to discharge the soil through the body. We developed drilling robot which is propelled like earthworms. This robot succeeded in vertical drilling of 430 millimeter into the ground underwater and bending drilling of 630 millimeter into dry ground. In this study, we may work on horizontal drilling as a next step. Next, let me talk about the drilling robot. This robot is composed of 2 units, an excavation unit and a propulsion unit. The function of excavation unit is excavating the ground and transporting the soil. Propulsion unit moves like an earthworm by pneumatic cylinder and lava tubes. The robot is propelled by a combination of sliding of pneumatic cylinder and expansion and contraction of lava tube. As shown in figure 1, at the state 1, all subunits were expanding. At the state 2, subunit 1 contracts and slides forward. At the stage 3, subunit 1 expands and subunit 2 contracts and slides forward. At the state 4, subunit 2 expands and subunit 3 contracts. At the state 5, subunit 1 and 2 slides backward. Then the robot propels forward relatively and penetrates the ground. Pneumatic cylinder of the propulsion unit propels the robot by sliding. Expanded units like this and grip the borehole, and contracted units like this and moves without friction with the borehole. Next, I like to talk about horizontal drilling. The characteristics of horizontal drilling are as follows. Drilling direction and gravitational direction are different, like figure 1, figure 6a. And both vertical and horizontal components of earth pressure applied like figure 6b. And propulsion does not increase depth. From these, we can say the following. The moment of gravity rotates the body of the robot, and difficult to model the stress on the gripping area and constant load on the gripping area. Expected problems in horizontal drilling are shown below. When the robot penetrates to the ground, gripping parts are biased forward. It is expected to cause the robot tilt upward, and this problem prevents the robot from moving horizontally. In addition, it is assumed that the propulsion units will not be able to grip the borehole due to the collapse of the hole, and thus propulsion will not be possible. So confirmation of these problems and clarification of the further problems that are needed. Then we developed the model of horizontal drilling. Objective of the modeling is considering the conditions under which the robot will tilt. Assumptions and conditions of the model are shown below. Considering the moment of penetration into the ground, like this state 5, considering the body of the robot to be rigid body, and assuming that upward tilt occurs like this. Modeling of robot during penetration is as shown in figure 7. The center of tilting will be point P. The moment MP around P is expressed by the following equation 1. The conditions for the absence of tilting are equation 2 to 4. And if equation 2 is not satisfied, robot tilts. If equation 3 or 4 are not satisfied, the hole will be deformed and robot tilts. Then horizontal drilling experiment was conducted. Objective of the experiment is as shown. And motor rotational speed is to 25 RPM, and the simulated ground is reddish soil ground. Let me talk about the experimental result. Figure 9 shows the relationship between excavated distance and time. Since the propulsion distance in one cycle was 0, operation was stopped at about 7,000 seconds. During each movement of the cylinder or aperture, backward movement occurred. Figure 10 shows the relationship between drilling torque and time. Drilling torque was stable throughout. Backward movement is the propulsion subunit was sliding before the expansion was complete, so the backward movement was happened. As for the drilling torque, the load was small due to slow propulsion, repeated forward and backward motion. And next, discussion about expected problems. The robot got unable to grip properly due to extended ground collapse, as shown in figure 11, that had occurred during the construction of the set was enlarged. But in real environment or rectangular soil tank, the collapse of the borehole, like figure 12, should occur. About the tilt of the robot, upward tilt occurred as expected. And due to the collapse of the ground, NQ0 got small and equation 4 was no longer satisfied. Finally, let me move on to conclusion. And we reached the following conclusions. We will plan to do the following future works. This is the end of my presentation. Thank you for your attention.
If you want, it's have as a last time. So please read this summary or conclusion.
And the summary is that the horizontal excavation was modeled, and horizontal excavation experiments in the cylindrical soil tank were conducted to discover problems in horizontal excavation. And the horizontal drilling performance of the current robot was confirmed. As a future works, experiments will be conducted in a rectangular soil tank to clarify further problems and consider and implement solution to deal with ground collapse, which is a problem during horizontal excavation. Thank you.
Okay, thank you. Interesting presentation. So do you have a question or comment from audience?
Yes, I have simple questions.
Yeah.
Maybe I missed something. As for the experiment, can you briefly introduce which kind of sand do you use in the experiment?
And the sand this time we used is reddish soil ground. This is similar to the regolith of the moon. Regolith of the moon, and it is excavate easily more than sea sand, ocean sand. So we use this soil.
Okay, thank you very much.
Thank you.
Any question or comment?
I have a question.
Please, yes, please.
Obviously, what you're trying to do is to mine for minerals, rare earths on seabed. So, I mean, is it necessary to drill into the soil to get to the minerals? Because there are lots of minerals which are just lying on the seabed, like, you know, nodules, etc. So what do you hope to actually drill down into and find what? How do you know that you found something?
It is now difficult problem. This robot does not have the sampling function and sampling unit or like this. And so this now in this step, the robot excavation excavation ability of the drilling robot should be improved. So in future works, sensing method for the sampling object should be developed, I think. That's okay?
Are you actually collecting the sample? So when you excavate it, do you pass it through the body of your drill so that you have a core sample available for analysis, maybe on the top somewhere on your ship? Is that sample actually collected, or are you just discarding it?
And did you mean that drilled soil could not be sampled in like this robot?
Okay. Because I think I saw earlier there was a talk about passing what you're drilling through the body of your robot. So if possible, then you could collect it in the sort of back end of your system. And if you, when you retrieve a robot, you could then analyze the core to see what is it composed of.
Maybe it's correct. Yeah, I think so.
Okay, thank you.
Thank you.
Okay, thank you very much.